Welcome to another video of Decoder. Today we are going to talk about a sorting algorithm that kind of breaks all the rules that you thought you knew about sorting. So today's topic is going to be counting sort. This is a very fast and seriously clever algorithm if you use it right. So without further ado, let's get into today's topic. You probably drilled into your head that on log n is the holy grail of sorting speed. I mean, it's the gold standard for heavy hitters like merge sort and quick sort, right? But what if I tell you that's not the whole story? What if there was a much more efficient way to sort? What if you could sort in linear time? This is what the counting sort algorithm does. In fact, this is its entire personality. Now, let's get into the why factor. The whole reason that on log n is seen as this theoretical speed limit is because of something called comparison sorts. They do exactly what you think they do. Comparison sorts compare the elements with one another. But the twist is that our counting sort doesn't do that. Counting sort belongs to a class of algorithms that get into linear time by ignoring the comparison between elements. And that brings us to the question, how do you sort something without comparing anything? The answer is in the name itself. We are not comparing, we are counting. Here is the official breakdown. Counting sort belongs to this class of algorithms called non-comparative sorts. What they do is that they sort integers by counting how many times they show up. And the coolest part is that it uses those counts to figure out where in the final sorted list that integers must come. So, the absolute key phrase to remember here is non-comparative sort. Simply picture this. You are making a histogram. You are not worried about which bar is taller than which for now though. You are just looking at each individual data piece by piece and making a tally mark. That's it. That's the core idea behind our counting sort algorithm. So the theory is one thing though. But now let's get our hands dirty and see how this works. We will be going through a step-by-step walkthrough with a real example in order to see how the magic happens. Now let's go to the starting point. Over here you can see a simple unsorted array where we have 6, 1, 7, 1, 3, 5 and a 4. Now the very first thing we have to do is figure out the range of our data. The smallest number we have is 1 and the largest number we have is 7. Consider it k. Now the first step is the counting phase. First we create a brand new array called the counting array. Now this array has to be big enough to hold all of the numbers we have in our input. So since the biggest number we have is 7, we are going to make the size of the array into 8. Now the array has indexes from 0 to 7. Then we just go through our input and start tallying. As you can see here, the index 1 has a value of 2 because we have two 1s in our input. Index 3 has a value of 1 and index 4 also has a value of 1. So you get how it goes. Now for the clever part, the magic step where we figure out how our algorithm ignores all those comparisons. We are going to take our count array and transform it into something that tells us the final position of each element. We do that by calculating what's called a cumulative sum. So to get this new cumulative array, we just update each spot to hold the cumulative counts of all the previous spots that it passed. But what does this tell us? We take a look at index 4. The cumulative value there is 4, which means that after we've placed all the numbers up to and including 4, they will fill up the first 4 spots in our array. So indices 0, 1, 2 and 3 are basically telling us the final end position for each of those elements they hold. And finally, like this, we have built our sorted array. Here's a really cool detail. We go through our original input array from right to left backwards. Why, you may ask? Because this is what makes the algorithm stable. Stable meaning that if you have identical elements like our two ones in here, their original order is kept in the final sorted array. That is a huge deal for some applications, especially when you are working with complex data. Now, like this, we finally have our perfectly sorted array. Well, if this thing is so fast, why don't we use it for everything? Well, everything has a catch. The incredible speed comes with some pretty strict rules and limitations. First, let's go over the advantages. The main advantage is the speed. It's got linear time complexity of O(n) plus k, where n is how many items you have and k is their range. If that range k is small, the algorithm is an absolute rocket with record times unmatchable by comparison algorithms. Plus, it is stable, which we saw was super useful, and honestly, the logic is pretty simple to get up and running. Now for the trade-offs, and they are quite major. The algorithm's speed and the memory footprint are totally dependent on the k value, which is the range. Imagine you have a tiny array with, let's say, 100 numbers, but one of those numbers is a million. Now you need a counting array with a million empty spots. That is a huge waste of memory, and suddenly that k value causes the entire process to slow down drastically. And of course, this sorting algorithm is built just for integers. So this brings out the question, what happens with the negative numbers? Don't worry, there's a pretty clever workaround here. You just shift all the data and you find the smallest negative number and you convert that into 0 and get that difference. And you use that difference as an offset to everything to make them all 0 or positive. Now we run that sort as usual and then subtract that offset we had back at the end. Now, as long as the range isn't gigantic, this process works like a charm. Okay, so with all the pros and cons that we talked about, where does the counting sort algorithm show up in the real world? Let's take a look at all the specific places that this algorithm is the undisputed champion. You'll find this algorithm doing this heavy lifting in some very specific spots. It's actually the secret sauce behind a more powerful algorithm called the radix sort. It's also perfect for sorting things with a small and predictable range, like let's say exam scores, which go from only 0 to 100. Or you can sort the characters based on their ASCII values. And of course, since it's all numbers and counting, it's natural for any kind of frequency analysis. So, what's the big takeaway here? It's that the best algorithm is not a one-size-fits-all solution. It all depends on your data. Counting sort is a fantastic reminder that sometimes the fastest way to sort isn't by comparing things one by one. It is to understand their overall distribution first. That's all for this video, and I guess it's the last video of this series as well. I hope we can meet through a new series that I'll be doing in the future. And until then, I wish you the best of luck. Thank you for watching.